Hi everyone, and welcome to the second lecture with Kürşat Sözer. The lecture will be about surgery approach and the Witten-Rashid to ref invariant. Please go ahead.
Thank you. Thank you again. Yeah, Tuesday in the first lecture, we covered algebraic preliminaries or quantum algebra fundamentals on most of the things on quantum algebra to prepare ourselves for this quantum invariance or three-dimensional TQFT constructions. Today, we will go with the surgery approach, which is also another name for it is the Witten-Rashid triad invariance, or shortly the common notation is WRT invariance. Okay, invariance. And this time I will use another book, which is the classic book in quantum topology by Vladimir Tryev. It's also called the Blue Book, they say, in quantum topology community. And then we will go over mostly again first part of this book, but of course the first part is about 300 pages maybe, but we will just cover just a few of topics and then very quick summary, and then also like we know some of the things that's covered in here, and then I will give, if you want to read, I will give some also maybe reading suggestions of what's going on in some of the chapters. But this is very classical book on TQFTs and everything written very, very super carefully and explained in length. Every constructions, operator invariance, and both algebra and topology, they're very carefully treated. Okay, let's change the gear from algebra from last time to just topology. Last time we never talked about topology, just only algebraic structures. Let's start with some very fundamental and central construction method in geometric topology, which is the modification of manifolds by doing surgeries and understanding behaviors and of manifolds. And if you want to classify them, this is very fundamental study in geometric topology. Of course, some one constructions or one method. And then how does the surgery on in the most general way it works? We fix an smooth n-dimensional manifold M. Okay, manifold itself is given. That is the manifold we are going to make a surgery operation, which is subject to change after the operation. And we fix an integer k. This integer is between 0 and n-1. What we do on a manifold, first manifold is kind of fixed. There's, I don't know, all the things that are going on, maybe some spheres, some dimensional other objects, there are homology classes, cohomology classes, homotopy groups, whatever. But what is the first step of doing surgery? Once we fix K, we consider this thickened sphere. We thicken such that the complementary dimension is n minus k, which adds up to n-dimensional manifold. N-dimensional manifold. So we embed this in here. This is like a tube because it's like a thickening of a sphere. And next, what we do after embedding this, we choose an embedding, and this after doing this embedding, we have some tube inside our manifold. Up to homeomorphism, diffeomorphism, we have a tube which is embedded, and then we get rid of the interior of this tube. We remove the interior of what is embedded. Now we consider SK cross inter. This is like we consider under embedding as a subset of M. we get rid of the interior. And now what is the boundary of the remaining manifold? Let's say M is closed. There is no other boundary. Let's say M is closed, there's no other boundary, then the boundary of this manifold is just Sk cross Skn minus 1, which is the boundary of this part, boundary of the embedded tube. And next, what we do, we glue to this boundary something else which has the same boundary. Now we are looking for manifolds, simple manifolds, which has this boundary and one direct thing that is the manifold that bounds the first component. But we embed it bounds, not we embed first, it bounds the second disk. Now we are getting interior of this disk out of the manifold, we get rid of it, and then we are attaching along the same boundary by filling out the second disk, the first disk. I can think of via some diffeomorphisms. Of course, these diffeomorphisms and embeddings are crucial. They depend, the resulting manifold depends. And then we get a new manifold. And this is not a, one may think of, okay, we embed something, we get rid of interior, and then we attach something else which has the same boundary. So one may think this is maybe some slight change. Not, in fact, there's a lot of changes going on, like homology group changes, homotopy group changes. One can kill homotopy groups, higher homotopy groups, whatever. So there's this is not like an isotopy or different embedding, different slight change in the manifold. In the topology, this whole operation makes a lot of change. And this operation is called the K+1 surgery because whatever we attach, this is attaching map of K+1 cell, K+1 handle. So this whole thing that embedding some tube, getting rid of interior, and attaching another one having the same boundary is called surgery. Let's see on a very simple example. Let n be a 2. So we consider surface and k equals 0. And let's consider M as a specific manifold just to sphere. So what do we embed? Here, k is 0. We are embedding S0 cross D2, which is just two disks, two disjoints. So we embed them on our manifold. Next step, we get rid of their interiors, right? So we get rid of their interiors. Now we have, what we have is like, this is our manifold. S2 minus 2, interior of 2 disks are removed. And now we are going to attach, what we are going to attach, k equals 0, if we look at this, we are going to attach D1 cross 2 minus 1, we are going to attach D1 cross S1. And there's a tube, right? Okay. This one is a circle, D1 is just a thickening of it. So we're attaching it along the boundary. We have a map. The boundary of this thing, if you look at it, the boundary of this thing is again 2 circles, which are the same as the boundary of what we removed. The boundary of this one is again 0 cross D1. This is boundary of this one is the same. So we attach it like this, let's say, and then we get a sphere with a handle, which is homeomorphic to a torus. So this operation, in this case, in 2-dimension, one surgery on a k equals 0, it makes a 1 surgery on a sphere, takes a sphere and turns it into a torus, which is totally different. It has nothing to do with sphere. They're not homeomorphic, they're not homotopic. So this is an example. I hope this will make it clear. But one may ask, what is the whole idea behind this? Where does one get this idea of removing something and adding it and getting totally different thing in a kind of controlled way? And that's the observation of this, that if you look at D1 cross D2, which is just a cube, right? This is homeomorphic to D3. When you consider its boundary is S0 cross D2, the boundary of the first one, and the other boundary is D1 cross S1, the boundary of the second one. And let's consider D1 is this direction and D2 is this square. Then look at this boundary. So what is the S0 cross D2? S0 cross D2 is just this left face and this one. And D1 cross S1, what it is? D1 cross S1 is precisely this. This is the S1. This is the boundary of here. This is the boundary of here, which we multiply by I, just this, which just gives this red part. And when you look at the boundary of this 3 cube is precisely S2, and it has precisely this decomposition. That's the whole idea. If you look at, that's where this thing, the first boundary of this product of two disks, is what we embed first, and we get rid of it, and then we look at, we embed the second boundary. And they share the same boundaries, because the boundary of this green part, right, is precisely this one, which is union of this. But they're, and same for this one, but their union of these pieces is precisely the boundaries of the red parts of the red boundaries. So this is the key idea behind it, and it's not special to dimensions 1 and 2. It's special. It will like get k n minus k, n minus k minus 1, k plus 1. We will see the same thing. That's the key observation behind the surgery, why it works. So surgery is very fundamental. Just to say a few words on it before moving on to quantum invariance. And surgery is crucial in geometric topology. It plays a very important role in higher dimensional classification of manifolds. It's a huge program initiated in the 60s and 70s, Browder-Novikov-Sullivan-Wall, with the surgery exact sequence and classification of higher dimensional manifolds. Involves crucially advanced techniques on surgery theory. A lot of theory developed on it. And plus, when surgery first introduced by Carver and Milner in their paper to understand exotic smooth structures on spheres and getting homotop sphere groups, it plays a crucial role to understanding these exotic smooth structures on manifolds and spheres in higher dimensions. And plus, not only in higher dimensions, these are kind of a higher dimensional topology areas. And then in low dimensional topology and not there, they play so crucial role in different things. Like here, I was not able to write people's name because there are so many, and then I cannot make misleading maybe things. But in quantum invariance, they play crucial role. Today we will see in Witten-Richtigen trial. And Hilgard-Fuller theory, they play crucial role. And hyperbolic 3-Manifolds by the work of Thurston, and also Seiberg-Witten invariance and the 4-dimensional manifold, they play important roles. So surgery is very central in various geometric topology constructions. Okay, I rewrite this again, maybe quickly going over again what we are doing. We are fixing a manifold. We start with a manifold and an integer. We embed a tube. We get rid of the interior of the tube, and we attach another manifold with having the same boundary. And now observe that we had before D1 cross D2. Let's go one dimension up. Okay? This is 4-dimensional manifold. And if you look at its boundary, it's hard to see, it's hard to draw for me the 4 cube. But by just mathematical computation, its boundary is S boundary of the first one, S1 cross D2, D2 cross S1. Like this is, we are going to embed this tube, this thickened three-dimensional thickened S circle. We're going to take circle and thicken it. We are going to have a tube around it. We are going to remove the inside of this circle or not, and then we're going to attach another thing. So in this case, n equals 3 and k equals 1. Before we had 2 and 0. We jumped up dimension by 1. And then m is again S3. So again, what we are doing, let's consider this is m. That I don't know. This is S3. That's underlying space that I cannot draw. R3 union point at infinity. Consider the first tube that we are going to embed. This is S1 cross D2. And in the core, like if you consider D2 as a disk around center, in the core of it, we have this point in here and a circle. That's the core of it, of this solid tori. Okay. In the core, we have a core. Now, when we embed it, what do we get? We get some nut. The core goes to some nut, embedding of a this core is just a circle. Embedding of a circle in S3 is just a nut by definition. And the solid tori is just a tube around that nut. And what is this information? We need to record this embedding carefully. It's not unique. There are various ways of embedding. Like we can embed a knot, but once we fix, even if we fix a knot, there are so many ways of embedding this tube. One can twist around it as many like as it is, and then we get the same. We get a different embedding. And this embedding data is precisely up to isotopy. Is precisely the framing of the knot. The knot, which is the embedding of the which is the embedding of the core of this solid tori. Now, if we consider, if you push off this core to the top of this boundary of the surface, we just push to the boundary. Now it lies on the boundary, and then we look at under this embedding what happens in here. This data just picking up one push off of a nut on the boundary, and its image under this embedding, it's going to tell us this isotopy, everything about the isotopic class of this embedding. It's, you may expect, or it must go like just all the way around near to the core. No, it doesn't have to. It can be, yes. It's not going to be like this. It's just not going to follow the not parallel all the way along. Depending on the embedding, it can get twist, it can turn around. And in fact, the isotopic class of this embedding of the knot, the tubular neighborhood of this core of the knot, is precisely how many times it turns around the knot. Like here, let's say we start in here, or let's say we start in here. We start in here, when we go, like this red part turns once around. So this tube around in the embedding, this tube gets one twisted around the knot, which is allowed when we do embedding. This is still an embedding. And then when we follow the knot, we get another twist. Then when we follow the knot again in here, we get yet another twist, which is possible. And similar to here, and this like one, we have 1, 2, 3, 4, the same way twist. Always, if you look at it, it goes around and turns right and come back. It goes around, turns right and come back. It can also go around and turns left and come back, but this is going to cancel with this one. So this can be say the framing in this case is some integer. In this case, it's 4. And this is the framing of the knot. And this framing is precisely the data of this embedding. This embedding up to isotopy. This doesn't depend anything but this embedding. That's very crucial when we do surgery. That's why I emphasize this a lot. So not embed a frame knot is this information. Knot itself, maybe in a parallel copy of itself on the little bit switched and how many times it wraps around. That thing is this information of this embedding of this solid tori. That's crucial because we are now, then what is the next step? We embed this and we know how does it embed it? How does this tube around the nut is embedded, tube around the core, this core goes to nut, and then how does the tube around the core is embedded up to isotopy. Next thing is the excise the interior. So we have this, we still have here in tube, right? So tube, now we get rid of this interior. Now we clean the interior, there is no red part. Okay, we get rid of the interior. So again, we have S3 and minus interior of this embedding. Okay, we have all the regions of outside in our manifold in S3 minus, but nothing inside. Okay, this is the boundary. This whole, this S1 cross S1 is the boundary of our current manifold. And that is S3 minus the thickened S3 minus the interior of the what is attached. So next, what we do, we have S1 cross S1 boundary. Okay, now we consider another, right? We consider the second, what we're going to embed, which has the same boundary, S1 cross S1. Now we are going to, we have S1 cross S1, which here we have a meridian, which bounds something, right? S1 cross 2, and then this meridian embeds this bounds, and then we attach this thing, okay, on the boundary. Look at the boundary of this thing, which is S1 cross S1, and we glue this boundary. Yes, it is different from blackboard framing. I didn't pay attention to that. Yes, one can think about blackboard framing. It's like 3. I just put a random example. You can say 7 or -1, depending on plus or minus. Now what we do, we attach this S1 cross S1 such that this whole red curve maps to this red one. That's the way we do it, because and this always exists because there's a curve on S1 cross S1, there's a curve on S1 cross S1, and there's always a map that maps this one bounding to this one. And the resulting manifold we denote as like, if whatever we start with K, this is the nut, K, in this case the trefoil. Okay, we consider this nut as a frame nut, and if you remember, framing encodes this thing. And once we do this in this process, this thing is unique, right? We say there's no kind of choice. Once we have the framing, we attach a solid tori such that this bounding circle maps to this framing of the link or framing of the nut. So there's this notation. So remember, a nut in S3 is an embedding of a circle into S3. And M component link in S3 is an embedding of, this is M many, of disjoint of circles into S3. Okay. Equivalently, framed nut in S3, okay, as we said here, is an embedding of S1 cross solid tori, is an embedding of solid tori whose core maps to the nut into this one. But this whole embedding data up to isotopy, as I said, is specified by an integer. Okay. And similarly, an M component framed link is an embedding of M disjoint union solid tori to S3. And again, when we consider this, let's say we have this unknot. In this case, we have unknot. And we consider, let's say it's framed unknot, so we need to write its frame. But either we write a frame like +1, or we are going to draw this whatever we had on the boundary, and how does it interact with it? Like, let's say we have a sphere, and then how does on the boundary of this solid tori it goes in here. Either we draw this, or we write non-nut +1. This +1 information encodes the solid tori embedding of the solid tori, or we can write like this. As if you look at it, if you consider this as a manifold. This whole operation, right, on the, you can encode it in here on the planar diagram. And plus and minuses is not here the usual combinations, right? Right-hand rule is like this. So there's a different formulations of framing of a knot. In general, people put like this, but in the quantum theory, since there's a huge connection between ribbon categories, we use this, and Thrive uses this as well. Okay, another example. Let's go to get familiar with the let's get familiar with the surgery theory. This in dimension 3. Like, let's consider unknot with 0 framing. Then what do we have? We have in the core of the solid tori and unknot, right? With maps and with this is an S3 and unknot, and then we get it of the interior. But since there is no interaction between them, there is no, it does not wrap around it in the solid tori. It's just the nearby, our knot is like this, and its framing is like this. Longitudinal movie is like this. But then we get rid of this part, and we are attaching this whole solid tori to inside, such that this boundary of the circle maps to this one. So, but if you remember, we still have S3 in here. Let's try to see what is the formatting manifold. So we are not attaching this disk in here because our manifold is already here. So we are kind of doing in the 4th dimension or interior of this thing that we are attaching the circle. So you can see there is some disk that bounds in here when we do this gluing, right? And then we are not filling it inside because we cannot map such a whole thing in the inside such that this maps to in here. But there is one disk in here coming from S3, right? In S3, there is one disk boundary on this, and one disk coming from this one, right? In the 4th dimension, in other dimension. And this is precisely S2 part of the resulting manifold. And similarly for any point in S3, this is the S1 part. So resulting manifold is S2 cross S3, S1. And another example is doing surgery on framed unknot with framing 1. Then in this case, our pushed off knot on the boundary is going to have this form. Well, the core is unknot. But then we are gluing a solid tori such that this maps onto this one. But in this case, we have yes S3 again outside. But we can glue this in a way that this maps to this, and this is precisely the dentivist of this thing along this curve. So we can glue the solid tori completely inside. So we fill back. We remove the inside, and then with this new other handle body, we fill it back. So result is S3 again. And same for -1 framing. One does the other way around twist, then one does the reverse of this dentivist. So given a framed link with M components in 3 sphere, and let Ni be the framing of the ith component, then what is the surgery on framed links? Again, we remove the tubular neighborhood. We remove the interior of the tubular neighborhood of the link. There are M many solid tori. We remove all of their interior, and we denote the resulting manifold as EL. And now we glue a new solid torus back in each component so that the meridian of this torus, which bounds on the torus, which maps to this chosen longitude, is the framing of the given knot. So this is the whole operation that we get, that one does a framed link on S3. And we're given a framed link on S3, that's how we derive a new manifold from S3. And Licorice and Wallace says, in fact, such an operation recovers all of the closed-oriented manifolds. Every closed-oriented or closed-connected orientable 3 manifold can be produced by surgery on some frame link in S3. So one can recover all such closed-oriented 3-manifolds in this way. So this is very important. And this is not unique. Different diagrams, different frame lengths in S3 can give same manifold. And Kirby's theorem answers this question: which two different links give the same manifold? And it is as follows: the two frame link diagrams yield diffeomorphic 3-manifolds if and only if they're related by two types of moves: Kirby 1 and Kirby 2 moves. And the first move is like add or remove disjoint unknot with framing ±1. Remember, doing a surgery on framing S1 plus frame unknot with plus or -1, we get S3. This is like get if, since this has no connection with other part of the link, it's just disjoint. We can just take inside this into some S3, and then we do a surgery on inside, and then we get another S3, and then we do connected sum. So this doesn't affect, this is not hard to see. Or the Kirby 2 move is like slide one component over another one. This is maybe a little slightly tricky to see. And to see it, let's fix a component of the link, ith component, and we want to slide it over. We will do K2 second Kirby move on it to another LJ, another component. And let's say there are many links and then they're connected or not, we don't know in the link diagram. They were some of them disjoint, some of them connected, but we fix the ith one and the jth one. What we do this cut in here, and then we do bend sum with the Li, but we don't do with this component Lj immediately. We do with its framing. Okay, this has some framing. Remember, we drew it before. This encodes this framing of Li. How does the solid toroid around Lj is twisted? And we do connected bend sum with this one. That's the operation that we employ. And what it says is like the Neve diagram is going to be like this, and the rest of the components have no change. Lj stays, Li becomes this one, and when we apply the surgery on this Neve frame link diagram, we get the same 3-manifold of the homeomorphism. Next, this is so far. This is maybe outside, not in the order of Trive's book, but Trive's in his book starts with this operator invariance of ribbon graphs and what is ribbon category. Let's remember again quickly what is a ribbon category. Let's C be a pivotal braided category. The left twist of C is a natural family of morphisms defined like this. They're just defined in this way. And they're defined, we have pivotal, we have duals in this diagram, which is very easy to write. But when we write algebraically, it's like this. And the right twist is of this form. It's again composition of 3 morphisms. And the ribbon category is the one where the left twist and right twist coincide, which we call the twist of this category. And ribbon graphs and their diagrams. So what is a ribbon graph in Trive's? Visually, these pictures are taken from this blue book. Trive takes many pages to describe it carefully. Like these are called coupons. Remember, for us, these are some morphisms in our category. Again, we are reading from top to bottom to top. Okay. And if, instead of like last time when we see on Tuesday, when we see graphical calculus on ribbon categories, we had just arcs. Now we replace them by bands. And we had just arcs. Now we replace them by bands. This is kind of similar. And ribbon KL graph in the language of Trive in R3 is an oriented where K and L are larger than 0. Surface embedded in the strip of thickened R2. Like we have R2 in here, we have R2 in here, and then they touch here transversely. There are many conditions, one page long of conditions, but they're all what is expected, being nice conditions. We get rid of all pathologies of the intersections, whatever. And then they look like this. And true one means in the bottom we have 2, and then top we have 1. And 0, 0 means there's nothing on the bottom, there's nothing on the top. And 2, 2 is like this. But you can see here there's a twist since we have a band. This is something that we didn't have in the graphical diagram. So if it is like this planar, what do I mean by planar? Like they can be set on some plane on R2 when we go in this direction. Then they're precisely, if you look at this, we can replace this with this one. With our graphical calculus, there's no change. But if we have something like this, if we have some twist in the band, we can turn it into, again, in this form, in this graphical calculus as well. How do we do this? If you look at this, that's precisely this formula when you do the isotopy. When you pull, when you take such a band and then pull this back, this is precisely this one, or equal to this one. So we can make again some, we can make it in a way that this lies in the just one plane in this height direction. So one is positive, one is negative, but they can, this twist on the band can be replaced by this kink moves. And the observation is that the theory of ribbon graphs, remember there is K input and L output, generalize the theory of framed oriented links in R3. And how does it work? To each ribbon 0, 0 graph, right, like this, is it here? To each ribbon 0, 0 graph, we can get a framed link. We may associate a framed link in R3. And in fact, this associating gives a bijection between the isotopic class of ribbon 0, 0 graphs consisting with just NLI, there's no coupons, there's no F's inside, and isotopic class of framed oriented links in R2 cross 0, 1. So this is what we do. Ribbon graphs are way more general than, in this respect, framed oriented links. Framed oriented links can be embedded into as 0, 0 ribbon graphs. Remember our graphical calculus. I will not go over it again, but just to remind you again what we had yesterday, we will follow it because we can replace, remember, we can replace these twists with something that can be new in the new formulation with these ones. And we have this as a left twist in our category, right? In the ribbon category. And in this case, the operator invariant of a C-colored link, the box, the arcs are what a C-colored means. C is a ribbon category. C-colored means the arcs are labeled by objects of X, objects of C, and boxes are labeled by morphisms in C, relevant to what is given above. When we have this intersection data, they are given by braidings. When we have these things, they are given by this twist in the category. Then when we have a link, that is a 0, 0 ribbon graph, then it is going to give some endomorphism of the unit object because it goes from unit object to unit object. We don't denote in our graphical calculus, we don't denote the unit object. So it's very compatible. So this is the operator invariant of C-colored graph, C-colored links in R3. But what we want way more than this. We don't want to, like, yes, one can study just invariant of links, framed links in R3, but the goal is to study invariants of 3 manifolds, closed 3 manifolds, and invariants of framed links in closed 3 manifolds. And that's this passage, this generalization. To be able to do this, ribbon categories are too general. We need to restrict, we need to impose more conditions. And all of these conditions, extra conditions, are just come together in this package, the modular tensor categories. So the upshot is so far, when you have a ribbon category, like a braided pivotal category, which admits when we have braided pivotal categories, we have this, we can write down left twist and right twist. If they are natural isomorphisms, and if they are equal, then we call it ribbon category. And whenever we have a ribbon category, we have an invariance of links in R3. That's the upshot. The goal is to generalize this invariance of links in R3 to invariance of closed-oriented 3-manifolds, and more invariance of links in closed-oriented 3-manifolds. And that's the content of algebraically the modular tensor categories. Let's go over Tuesday's lecture quickly. A category is k-linear if home sets are k-linear and functors is k-linear on home sets. And direct sum just imitates whatever we have in category of modules or category of vector spaces using projections and inclusions, expected equalities. And the category is additive if it is closed under this direct sum operation. And an object is called simple if its endomorphism is just free of rank 1. And if, remember, a prefusion K category is the one that admits a collection of objects, which contains the one collection of simple objects. The unit object is a simple object. And whenever we pick two different objects in this collection, there is no morphism between them except the 0. And every object is a direct sum of finite family of objects in I. This is what triads calls domination. So this collection of simple sets, this collection of simple objects dominate the category under direct sum. And in this case, when we have such a set of simple objects, it's called representative set of simple objects. And the fusion category is the one such that this set is finite. And when we make an analogy between fusion categories or prefusion fusion categories and representation theory, one should consider simple objects as irreducible representations. And dimension that we know, multiplication of left and right, if we have spherical dimension of a category, is given by sum of dimension squares of simple objects representatives. And next, modular tensor categories, when we fix a twist was like this, or like this, but this goes from when we fix I, a simple object, this is a morphism from I to I, but since I is a simple object, it's just like K. So twist is about having some numerical, some element in the commutative ring. The twist data is equal to this one in this case. When we pick a representative set, we define this plus minus delta in this form. And the category is called anomaly free if they're equal. And next and last is the definition of S matrix. S matrix is a square matrix, of size, set of representative simple objects. If there are n simple objects in this representation, it's n by n matrix. Whose entries are given by linking I and j simple objects in this Hofling version. And this is again endomorphism of 1. This is K, so it's just a number. So we get a S matrix, and the category is called modular if this matrix is invertible. And the dimension has this condition. Okay. Once we remind ourselves or recall modular tensor category definition, let's see how does this invariance work. Let's see Bn. Maybe maybe before starting here, because maybe we can give a 10-minute break and then start from here if that works. And so far, what we have done, we learned surgery on a frame length, and then we learned that every close connected orientable 3-manifold can be get in this way. And then we just reviewed again all the algebraic preliminaries on this construction of Witten Vecherekin triinvariants. Now let's consider C, let's fix an anomaly-free modular tensor category. It doesn't have to be, by the way, definitely. We don't have to choose anomaly-free. Remember, anomaly-free means this is equal to this, and their formula are given here. It doesn't have to be like this, but for simplicity, I assume this one. Without this one, the formula is just a little bit complicated, and then one needs to formulate, one needs to think of this 3-manifold as a boundary of 4 manifolds, and then the signature of the 4 manifolds involves that I don't want to get into that. That's why I restrict myself to this one, but it doesn't have to be. Okay. And with this formula, again, we have the statement. And then now let M be a closed oriented 3-manifold and connected, let's say. And R be a C-colored ribbon link inside M. And by Licorice-Wallace theorem, we know that there exists a frame link, let's say n many components, frame link in S3, such that when we do surgery on this link, we get M. And the C-colored ribbon link in R prime is the complement of this link, such that the surgery on L turns the pair SR, S3, R prime into MR, at least up to homomorphism. So the question may be why R changes from, why does the ribbon link changes from R to R prime? Well, here the observation is this: when we have our link that we do no surgery on S2, S3 to get M, if we have our links in here and our frame ribbon link, if we have a frame link, is totally away from, disjoint from the other one. Okay, so maybe if we have some links in here, L1, Li, whatever, this one, and if R is totally away from it, then it's unlinked from all of them, then R prime equals R. Okay? It doesn't change. If R is just totally away from this link component that we do surgery on S3 so that we get M, then R and R prime are the same. They don't change. But if R is R in M, the corresponding R prime, if this is linked with surgery, then when we do the surgery on S3, then, you know, as you have seen in the examples, it changes the topology a lot. So it can get rid of some part of it. It can introduce some more relations. It can change it. It can get another frame. It can get another one. So it is this change that happens if this ribbon link is linked with the link that we do surgery. Then it's subject to change potentially because of we don't know what's gonna happen on this surgery part. Maybe we get rid of some part that does make it simpler, and then we get simplified version. But if this ribbon link is way away from and unlinked from the collection of like the link that we do surgery, then it's the same. So the idea when we have 3-manifold and the ribbon link inside, we reduce the ribbon link in link and the ribbon link in S3. So we orient link arbitrarily, and then we say the coloring of this link is the set of maps from, remember, this is a number of components. So the coloring of the link is precisely assigning to each component a simple object. That's what we do. We have a link, and for each component, we assign one simple object I1, another one I2, and that's going to be a coloring. It's like a state in physics. For each such assignment is like a state, and then what we do, we consider all possible such assignments. And for each lambda in color, for each coloring, the pair, any question? Sorry. Yeah, for any coloring, we consider this L union R prime, which is a ribbon link, right, in S3. And so we get a C-colored ribbon ring in S3. So what do we know? Whenever we have a C-colored ribbon ring, we have its operator invariant. The ribbon graph, or equivalently in Tribe's notation, is a 0-0 ribbon graph, but we start with a modular tensor category, right? It's in particular a ribbon category. So for this one, we get its operator invariant, so we get a number. For each such coloring, we get a number. It's operator invariant. And now what we do is we do sum over all such things over all colorings, which in a normalized way. We normalize with dimension of this simple object on each component. Okay. On each component, we do this computation. We assign a simple object for each coloring. We have a coloring is an assignment of simple object to each component of the link. And we do this assignment once, and then we take product of all these simple objects indexed by the components of the link, because each component is some simple object. They can repeat or not, but we take their dimensions. We know what it is. This is an object, right? Simple object in C. So when we have an object in a modular tensor category or pivotal category, we can take its dimension. Remember, it's just this one. Right? So and this is again endomorphism of one, but we know one is the fact that modularity implies fusion. One is simple. So it says this is again some numerical. And this is also number. And then we take product, and then this is that we already defined. Delta, delta plus, delta minus. So if it was not anomaly free, what was going to happen is we had some delta minus 1, and we are going to choose square root of dim C square. So D trial denotes this V, and D to the sigma x minus 2 times this thing. So sigma x is going to be, if I'm not wrong, this was the x is the 4-manifold bounding M. It's going to be the intersection. It has 4-manifold close, like it has an intersection form. Intersection form is a matrix. We consider its signature, and then we do this normalization. But when we have anomaly free, it reduces to this form. Or you can look at the tribes for more detail. But for physicists, maybe this equation, this thing is more familiar. Assigning something to some coloring, like coloring is like giving a state and then summing over all of them. And finiteness is crucial to make it well defined. And Bescherigen triad and triad, their theorem is that this assignment, this numerical number assigned to and yeah, before that, one can consider this empty. This is the most general version. We don't have to consider ribbon link or ribbon graph in our manifold. It's an extra thing. If we don't consider, we just get an invariant of closed manifold. It doesn't change anything. If you look at it, it doesn't change anything. It just adds this. Otherwise, we just look at the link from which we obtain M by doing surgery. So if we take this empty, this is going to be empty, and then we are going to get numerical invariant of our manifold. So R can be empty or not. And the theorem is this is topological invariant of this pair. So what is topological invariant of the pair is that if there exists a homeomorphism, if there is another pair, N and S, closed-oriented 3-manifold, and a ribbon graph, if there exists an homeomorphism and an isotopy, same time, taking M to N and then R to S in this identification. So this is a, even though statement is short, this is a very strong theorem in the sense that one needs to show it is independent of everything, every choice that one made. It is independent of L that we choose. It is independent of I that we have in the modular tensor category, because modular tensor category doesn't come quite with I. Like it has simple objects, but one needs to choose representative set, but it's independent of that. One needs to show it's independent of all of the choices that has been done. And it is invariant. And this one, there are different normalizations, and this normalization is done in a way that S1 cross S2, the value in any case, in any category is 1, and for any tensor category. And S3 is delta minus 1. And in his book, Trial says, in this normalization, this tau agrees with earlier work of Witten's 3-manifold invariant given by path integral. Like especially because when they first study into this invariance, they don't do this in this general. That's why I put trial extra when his published they generalize. When in the early work, they, if I'm not wrong, they do everything on this modular tensor category with some roots of unity. 2 pi I, some roots of unity. They do and this, and then Trial in his book extends this thing. And then this invariant agrees with Witten's Chern-Simons theory integral in his famous work. If we consider length space computation, length space of N1, the length space N1 can be obtained from S3 by doing surgery at trivial knot with framing N. Have this N. So we can compute this. We can see this. I remember there are various ways of denoting the frame. And one way is if I do this, no. Yes, this is plus. We can consider like this, right? This is n kings, there are n, and they're all of them are pluses. This is plus, into this plus 1, and plus 1. And remember, when we color this, like there's only one, there are maybe, we don't know how many simple objects in the category, but what do we know? There is only one link component. So in this formula, n equals 1, right? This n for us is 1. So we assign to this color some simple object I in I. But then for this I, we have this is a ribbon category. So theta left or theta I is I times 1, right? An endomorphism of I. Oops, it's VI. Since I is a simple object, This is K, right? And we have this, since it's invertible, we have this invertible numbers which are framing, which are twist invariants. But then what we do when we assign to this, we apply this vi to the n many times. We just product. This is like, this brings us vi to the n. And then we take, and this is multiplicative, and then we take its dimension, right? We take its trace. This is vi to the n times dim I. And that's exactly coming from here. Like, we have dimension in here, but this graph calculus is also dimension I. And we also have dimension I in here, like vi to the n, vi to the n coming from here. Then we get this formula. And here we have, yes, n is, we have one component, makes delta minus 2. So it works. For length spaces, the formula works. And the opposite orientation length space can be obtained from 3 sphere by Sergio along the trivial knot with minus n framing. And then we do the same thing that I did above, but maybe now it's even simpler because to the drawing. So now they are minus ones, but each of them is going to bring multiplication with vi minus 1. And we are going to get this vi minus n in this case. Okay, we know that sphere can be obtained as framed unknot with frame 1, or empty link diagram. One can formally define the surgery on an empty link diagram, which means doing nothing, and so we get S1, or plus or minus 1. We know unknot with framing plus or minus 1, doing surgery on it. We have seen that it is S3 again. But in this case, what is the invariant? This one is clear because m, there is nothing to do in here, just 1, and n is just 0. It's just delta minus 1. On the other hand, we have this. So operator invariant is going to be just dimension. And we have another one. We have minus 1, is 2. We have one component. And we have, again, this, yes, this is plus 1. So this is our L, right, frame diagram. But this part is going to bring vi, and operator invariant of this link is going to be vi of dimension of I. And then we have just one assignment, and then we have this dim I as well. So we get this formula in the case of S3. Now about the proof. Like I told at the beginning that this Kirby's theorem after Licorice-Wallace. Remember, Licorice-Wallace says every close connected orientable 3-manifold can be obtained as a surgery for some frame link in S3. And the Kirby theorem says whenever they are related by these two moves, then they are whenever the framed links are related by these two moves, that the Kirby 1 and Kirby 2, they are the resulting manifolds under surgery is going to be homeomorphic. But Troyev says he doesn't in the book, proving invariance under this Kirby 1 and Kirby 2, like blowing ups and blowing downs, plus Kirby 2 handle slides, especially in this handle slide, it is very tricky because when you do handle slide on other diagrams, you cannot simplify this as a composition of simple things because links can be crazy, and then you cannot, like when you want to do proof in this most extreme generality of sliding link component to other one and then trying to understand the resulting link and the making relationship between the initial link is very hard, because when we slide over a complex component, it grabs all of the framing and the resulting link. How does it simplify? How does it get complicated? It's very hard. But instead of like and I also didn't know invariance proved under this one, and Try also says he does not proof showing that this invariant this number is invariant under K2, but there's an alternative way by Van Roorker moves, which follow certain patterns. There again, these two, they are moves on frame links generating same equivalence relation. So this generating equivalence relation is like L equal to L prime if S3L is homeomorphic to S3L prime. That's the equivalence relation. And then, but in this case, Van and Roorker moves they follow certain patterns, and they can be stated as composition of simple tangle generators, just like McMaster moves. So, and then he uses this Kirby Van Roorker moves. And what are they? They are just one type. Okay, Try represents the Kirby moves in the form of Van Roorker in terms of link diagrams. Like when we have a diagram and when we have a +1 curve around it, like this, and R twist, then this gets simplified into just usual identity of this each part. These are just, in this case, this means how many components are there. They're just identity components. So it's like getting rid of this this component of a link with framed 1 is about to having R many twists. And here R has to do with this R entries. So I mean, this as a morphism, it goes from some V in the category like X1 tensor, X2 tensor, XR to something. Maybe in this case again, Y1 tensor, YR. In this case, let's consider the examples. When R equals 0, we have this move. There is no arc in this case. There is no arc. This is precisely Kirby 1 move. But in his book, he refers to this as special Kirby 1 move. Getting rid of this one to empty diagram or empty diagram. So this one is called special Kirby move. When R equals 1, what do we have? We have just one morphism and a one twist. And then this, get rid of this one and we get identity of this morphism. Or when we have two arcs, then this is equivalent to having like we could have this diagram and then two twists in here like this, two R twists, but this was going to be equal to identity, but then instead of putting in here, he puts in here and then cancels with this one. And the theorem is two closed-oriented 3-manifolds obtained from S3 by surgery along framed links L and L prime are homeomorphic if and only if this L prime can be obtained from L by finite sequence of Kirby 1 moves and special Kirby -1 moves. And special Kirby 1 moves are like this, and Kirby 1 move is this one by doing this ones. This is, since it's an if and only if statement, it is enough to show that the invariant, this numerical invariant is the numerical scalar that is associated to manifold with a ribbon link inside is invariant under this move. And then he does prove this by step by using various lemmas, the invariance under this thing, this move. And so far, what is this described in here? This is just a manifold obtained from S3 from links. There is no ribbons, extra ribbons inside. If you look at this is a special case, and Tribe and Reshetekin, they generalize this to framed linked equipped with ribbon graph inside. So the first one gives this one. This is kind of context in here. And the additional thing, if we fix another ribbon graph, then this generalized curve removes satisfies this theorem again with this under this generalization. So that's the content of their theorem. A pair consisting of a closed-oriented 3-manifold and a ribbon graph considered up to homeomorphism can be obtained by a surgery on S3 along some pair, a framed link, and a ribbon graph. And the result of the surgery on this pair is preserved under this Kirby moves on this ones. And these moves are no different than this ones actually. By generalized, I mean, because ribbon graph is the same, except in the ribbon graph, there may be some boxes that coming from, because this is a link, this is just, there's twists and braiding, there's nothing else, but ribbon graph may have some boxes with labels in the category, morphisms in the category, but since everything like braiding and twist, they're all natural, whenever we do these moves, we can get rid of these boxes away from them. And when we make it away from them, we can exhibit these operations on the part that doesn't have any of the boxes in the category. And conversely, this is the hardest part. If the results of the surgery along two such pairs are homeomorphic to when we have L omega and L prime omega prime, if the surgeries are the same, then these two pairs are related by these moves. So they're kind of a complete set generating the relations between these pairs producing closed-oriented 3-manifolds with a ribbon graph inside. So these theorems reduce the study of ribbon graphs in closed-oriented 3-manifolds to study of pairs in S3, which is very, very neat. Up to relations. Study of pairs in here up to these relations. And then otherwise, studying things in oriented 3-manifolds is very, very hard. Well, this is the things that I wanted to say on the kind of proof side of the things. How does the proof goes? And next, what I want to say, this written Reshetekin triad invariants give an action of SL2Z, projective linear representations of SL2Z. We call it S matrix. Their invariants are all things, I and J, and the morphism of I. Whenever we are given a modular tensor category, we have an S matrix, and the fact that it's modular means it is invertible. Then using S, one can construct a projective linear representation of SL2Z. How do we do that? Then not only S, we need to introduce two more matrices. First one is the T matrix. This matrix is diagonal matrix, where diagonals, remember, these rows and columns are indexed by the representative set of simple objects. In this case, the diagonal entries are precisely the twist scalars. And the involutive square matrix, which is just whether it's duly equal to J. But then these are not easy. These are lemmas and propositions in the book to get these relationships. S square is equal to delta square times J. And delta inverse STS has this relation, these two relations are obtained after careful study of the structures given by the invariants. On the other hand, SL2Z has this representation of two elements with two relations. And under this information, sending S to delta inverse S, the S matrix, and T to T inverse defines a projective representation of projective linear representation of SL2Z. So this is I don't know much about it, but this is kind of connection between relationship between modular tensor categories, and modular groups. This is kind of a modular group. I'm sure it is very interesting thing in number theory. And understanding its representation, I believe, is important in number theory. And then modular categories leads to representations of modular groups. And as you see, this is not something specific example. For any modular tensor category, you get a projective linear representation. So this is like this VRT machinery is like when you get input, you get a modular representation of modular group. Now here I want to remind you again, in the last lecture, I told you again, but here with a little bit more detail, axiomatic definition of TQFT. This is definition by Atiyah. And okay, let's say three-dimensional 3D TQFT is a symmetric monoidal alter from three-dimensional cobordism category to category of vector spaces. So what are the objects here? Objects, closed oriented surfaces, and morphisms, oriented cobordisms. Up to diffeomorphism real boundary. So, like what it does in general, we have a surface and we have a cobordism, another surface, three-dimensional, say sigma 1, sigma 2, if you read from Latam, and then this is the three manifold that bounds them. So what Z does, so it sends, this is the category of vector spaces, and linear to K-linear transformations, linear maps. So under Z is going to be sigma 2, some vector space, going to be C, sigma 1 is a K vector space. And then any cobordism is going to give us a linear map. There's like state spaces and then maybe time evolution or something, like linear map between these linear spaces. And they must be finite dimensional vector spaces because of duality condition. Well, as we discussed last time, whenever we cut this along appropriate codimension manifold, it can have some genus. I don't know how many, we don't know. But this says this diagram decomposes as sigma 3 doesn't find. We have this commutative diagram. But another important thing, this is kind of, we have not used yet symmetric monoidal structure. This is so far is just about Z being functor. So Z being monoidal functor, what does it say? That's extra says whenever we have two disjoint union of surfaces, then this is going to be right isomorphic to Z sigma Z sigma prime. Remember, when we have Z as a monosymmetric monoidal functor, it has three components. Z itself, we have Z0 and Z2. Remember, Z0 is going from Z1 to the 1 prime of the target category, and Z2, remember, Z2xy is an isomorphism. This is going to be isomorphism, and Zx tensor Zy to Zx tensor y. Now we are using this isomorphism is Z2 in this case. And now what does Z0 says? What is the unit object in cobordism category under disjoint union operation? It is the empty manifold. So, and what is the unit object in category vector spaces? It is a one-dimensional vector space. Canonical vector space is K. So, and we have this, and similarly Z2 says, right? And similarly, when we have cobordisms, B prime, same as Z V tensor V. But if you consider now consider closed, let M be a closed oriented 3-manifold. So then I will draw it like this. I don't know how to do it, but it's closed. It doesn't have any boundary. So as a cobordism from where, what is its source? What is as an, so it is an element in COP3. And since it's a 3-manifold, it is not an object, it's a morphism. So M is a morphism from where to where? That's we need to ask. Since it doesn't have any boundary, it's a morphism from empty manifold to empty manifold. It's a morphism from unit to unit. But under Z, where does it go? Under Z, up to isomorphism, this goes to K. Under Z, this goes to K. Under the Z0 identification, remember, this is Z0 of the monoidal functor. And under Z0 isomorphism, this goes to K. And so ZM is just a linear map from K to K. But such a linear map always determined as by the image of, right, ZM1. It's enough to say what it does to one because it's a linear map. And this map is some scalar, right? And this is the quantum invariant of closed manifold. This is the numerical quantum invariant of M. And in the case of surgery, this is the claim is Z, when we put modular tensor category M with empty ribbon graph, let's say, okay, we don't put empty ribbon, we don't consider ribbon graph yet. Then this is, remember, is an element in K. This is this number written Rashidin triad invariant of closed 3-manifold. Or for Witten's perspective, this is the path integral over a kind of certain quantized Chern-Simons functional over the manifold over the states and the number. So this is the invariant. Like whenever we have TQFT, it assigns three-dimensional TQFT. It assigns numerical invariance to closed 3-manifolds. So you may ask, what are the vector spaces associated to surfaces? Okay, this is not that easy. If you look at Tribe's book, actually there are a lot of information if you want to get rid of these anomalies, if you want to make anomaly freeze. Also, if you look at the Witten's paper, there is always in the surfaces there are punctures. This ribbon graphs goes through the surface. Whenever you pick a surface, you need to put n many punctures. They go through it, and then around those punctures, you need to choose Lagrangians and Maslow indices. With these indices, it's a well-defined TQFT. Without, it's kind of a projective TQFT. These vector spaces define up to plus minus. So there's this caveat there. You can look at and read from the Tribe's book. There must be some choices must be made for surfaces with punctures. But in general, as what to get from this diagram, we can still answer this question. It's roughly like if we just consider surfaces, not like surfaces with kind of punctures, it is kind of like this. C is a modular tensor category. And let I be the set of representatives of simple objects. Then we consider, let's say, this direct sum. I is an I do I. Okay. This is still an object of C. Okay. This is called the coend of category C. Okay. So we take each simple object in the representative set, each simple object with tensor with its dual, and we take direct sum of these things. And for tau, like now Z, for me now it's tau, right? For us, like we define tau M. What I want to say is here, tau C. So for me, the functor now is not Z, but the Z was the most general case for any TQFT, whatever. Now I consider tau. Tau means the written Rashidin tribe invariant. Now, what is tau sigma G? Okay, closed oriented surface of genus G. So what is which vector space it is? It is isomorphic to C rho 1 to tensor product of C to G. Okay. This is G times tensor product of this coend. This is maybe this is kind of the vector space one associates to a surface. And reality and Berkeley, they have this coend formulation, which is nicely Myself thinks works. Well, it's a little bit categorical thing, but it's a nice framework for understanding the surfaces. Okay, this is kind of what I want to say. Okay, before moving on from here, I want to say a few words. And again, there is not like, well, I should have said theorem. This is again TQF. This book T C M R, or let's say R, is 3D TQFT. Before the earlier theorem, remember, it says this number, sorry, extends to. The previous theorem says for any closed 3 manifolds, it gives a number. And then if you have disconnected manifolds, this number is multiplicative. So whenever you have such an invariant of closed manifolds, some invariant which is multiplicative under disjoint union, then you ask this question: does it come from a TQFT? Because whenever you have multiplicative numerical invariance, that's the question: can we generalize this invariant to a functor? Because you think of yourself like having something defined on this on this morphism category, on this collection of morphism in the category, cobordism category. For everything in here, you put a number, and if you take their disjoint union, if you take their monoidal product, it's monoidal product in the result, right? In fact, category vector space is tensor product of numbers is just multiplication. So whenever you have whenever you have multiplicative invariance of closed manifolds, you ask, can we extend it to a TQFT? Can we extend it to a, from this data, having this to some k, every morphism to k, you ask yourself, can we make this to extend to this thing? Can we assign coherently to surfaces such that it behaves like we assign some vector spaces to surfaces? Can we assign something to cobordism between manifolds such that the closed manifolds are given like this in a way that it behaves well under composition, which is gluing? That's the question. And then this extension is not an easy job, and it works. But as I said, that's what I was going to say. Whenever you have multiplicative invariant of closed manifolds, like multiplicative under disjoint union, one should immediately ask, can we generalize it, extend it to TQFT? This is kind of question. It's not like coming from functor to other way. Like we always do this, like we define TQFT as a functor from this thing, but it's not like this. We first get this construction. If you have a nice invariant, this numerical thing, and then we say, can we extend it to surfaces which behaves very nicely, which behaves functorially? That's a crucial part of the TQFT or quantum topology part. And try answers is as yes for this one. And this is kind of roughly the answer. But of course, there are a lot of details in it. If you look at this one. Well, as in maybe some applications or things, quantum representations of mapping class groups. Like when we fix a closed oriented surface of genus G, then there is a very well-known study of symmetry groups, which is a group of mapping class groups called group of isotopic class of orientation preserving self-homeomorphisms of this surface. And it is very well studied in the closed surfaces, surface with functors. There's a lot of unknown, but its representations are also very important in hyperbolic geometry, taking their theory, moduli spaces and things, and many other things. And quantum, whenever we have a TQFT, three-dimensional TQFT, it leads to a representation of such of these groups. And how does it work? Well, where does a representation of a symmetric group of a surface come? It is coming from this mapping cylinder construction. for any mapping class group, we can form what we do, we have a surface, let's say just G. We take its product, I, and we take it sigma cross I, and here we parameterize with identity. Here we parameterize with alpha. So this manifold is not this is like M alpha. This is mapping cylinder. So this is different than sigma cross I. Sigma cross I is identity in cobordism category. Like sigma cross I is the identity of sigma in cobordism 3. Well, in home sigma to sigma, right? So whenever we have a three-dimensional TQFT, when we apply to this thing, right? If alpha was identity, then this was going to be just identity between the vector spaces assigned to that. Like in this case, we have sigma 2, let's say alpha, so different parameterization. We have just usual sigma 2. Oops, we are going from, this is sigma m alpha. Right? And this is a vector space. This is a vector space. And when you have another presentation, you do the same thing. And then this, when we have another presentation, beta, like this is parameterized with alpha. Now this is parameterized with alpha compose beta. And we glue, and we do this. This is sigma 2, and the parameterization to this one is by alpha compose beta. And then they works perfectly. Oops. So it is, and these are linear maps given by. So the point is, whenever we have these symmetries, we construct these mapping cylinders, and there are some different cobordisms. If the homomorphism is not the identity, then we consider their corresponding their images in vector spaces under this three-dimensional TQFTs. So this is the representations of mapping class groups given by TQFTs. This is precise, and this defines a projective linear representation. This again issue of Maslow indices, choosing Maslow indices, and Lagrangians. I can read. We don't get a full-fledged representation, but just project them, something defined up to pluses, minuses. There's some, and remember that when we consider, and it's not any surface but torus, its mapping class group is SL2Z generated by then twist along longitudinal meridian. And then this quantum representation given by Wittgenstein triad TQFT, surgery TQFT, is precisely the one that is given described above. And I didn't have time to prepare. There are actually results on this. A lot of work on this have been done in 19 and early 2000s. People study images of this dentist because these groups has a really nice presentations in terms of dentist. And then they study their images under this S matrix and T matrices. It's enough to know in general under this. And then, if I'm not wrong, they're in general kind of finite order. They cannot, if they cannot, does not capture everything. But we will see hopefully in the last lecture that what we have seen so far, it's semi-simple modular categories, And there's a non-semi-simple extension of this theory. And then which generalizes algebraic constructions. There are interesting recent results on these quantum representations capturing interesting information, much as I know. So I can talk about this, but this is something that happens whenever you have a three-dimensional TQF. You can consider grouping class group representations and derive some data from them. And yeah, that's all I want to say today. Thank you for your attention.